Good afternoon, everyone. I'll start with the last lecture, and this is just a revision time. I'll continue with more problems with view factors. Start short window. The first problem, which where we have two surfaces, one and two. Is my screen visible? Kirti Singh, is my screen visible? Okay. So we have two surfaces, one and two, and they are separated by a distance of 0.7 L. Then both the surfaces are square in nature. Okay, they have the same sides, and all the sides are of L length. So this is surface one, this is surface two. Now we have to find out what is F12 for the squares shown in the figure. View factor F12. How much one is radiating and which is received by the surface two. Okay, so far whatever we have discussed in the previous lectures, the view factor problems, they were solely based on the area and on the intuition. I mean the how much should be the F or the view factors for one surface to the other. Some are 1, some are 0. Okay, some due to symmetry, some are zero point 0.5. If there are two surfaces and they're symmetric to each other, they can then we can consider zero point 0.5. So, but for some uh, certain set of these surfaces, there are few plots already available in the books or available. So you can see from there also what is the view factor. So this plots is available for few combinations. Okay, just like this only. This almost it has this. We can mimic this system with our problem. This system, and somewhere we will come across this is also another system. So there are already a few graphs which are available to us. From there we can calculate the view factors. So our system was like this. So we can extend this figure in such a way. This is one, this is two. Now if I extend this one, and also if I extend this two to this side, so this become the bottom part becomes whole one surface, and this top also we can consider it as another surface. So we will name this surfaces. The top one will be, top right will be 3, but we can consider 4 also. This is 3. The bottom one is 3, top one is 4. Okay, then we can mimic this as this one. So here the top surface is x, sorry, one side of the top surface is x, another side is the y for rectangle. But in case of square, both x and y are same, and d is the distance between the two surfaces. So what they have this y by d ratio, and another is the x by d ratio. If we have, then we can directly calculate f1, 2, where this one is the upper surface, 2 is the below surface. So we'll calculate the x by d and y by d in our case. X is the this one. This is x, and this is y. So x by d we have x is, since one side is L, so it is just double the L, so twice of L divided by d. D is this distance between the two surfaces, that's 0.7. So we have this 0.86, and y by d is just L divided by 7, 0.7, L is 1.43. Now we have to do some, we have to play with this geometry here. We can write this as this A14. This whole one, it can be considered as the area of this whole one can be considered as A14. Just denote it by A14. I write A14 vector A142 to 3 or 32. That means the energy emitted by 1 4 and received by 3 2. This can be written as A1. This is the total radiation. Okay, so A1, it can be received by 3 and it can also be received by 2. It can also be received by 4, but then A14 is 0 because they are on the same plane. Similarly, A41 is also 0. But this is received by 3 and 2, so we can write as A1 F12 and write. So received by the surface 3 and then also A4. Similarly, we can write for A4, A emitted by 4 and received by 2, A4 emitted by 4 and received by 3. Like this. If A41 is again 0 because they're on the same plane, then we can write this as A1, A1, A4, A4. All these are same actually. I just double the surface of A1 on the top side, so it is A4 is equal to A1. Also, all are same. All are the same surface layers. So we can write like this. So I can take A1 common here from all. Then I can write F12 plus F2 step plus. Now we have F. Now how 4 is looking at 3 and how 1 is looking at 2, they are the same. Okay, so we can write F3 is equal to F1, 2. And also 1 and 3, 4 and 2. These are also same. F1 is equal to F4. So instead of F43, we can write F12, and instead of F42, we can write F10. Step is A1 instead of F4, we can write 1. Instead of F43, we can write F1. So it is price of F1. That's price of F20. Now this F1, 4 and 2, 3 can also be written as this A14. This can be written as, since it is A1 this and this, so it can be this A14 can be written as total A14 can be written as A1 plus A4. A4 is also the same as A1, so we can write it as twice A1. So this thing we can write as twice A1. Twice A1. F1, 4, 3. This is equal to A1 twice. 2 will come from this 2 and 2 will get cancelled. A1, A1 will get cancelled. So we get this F1, 4 plus S. F1 plus. Now from this figure we have, so we have to individually find out this. The question was that we have to find F12 for the square shown in the figure. So we have to find this out. Now from the graph plot, we can find out what is this F13 and also F1423. How do we find that out? So this will directly give F1423. From here we can get, because we are considering the whole this double surface. So this will give us F1. So x by d we have 2.86, y by d we have 1.43. 2.46 is there, 0.5, so around 2.46 around here only. And y by d is 1.43. 1.43. That means almost here. So if I draw the straight line from here, it's not straight. But in such case, this graph should be provided to you if if anyhow this questions, this such questions come in exam. So if I extend this, we directly get this F143 here, and it should come around 0.38. This depends on your graph paper and how you are plotting. So whatever value you are getting on the y-axis, that will be F14223. So this is 0.38, and this we get from, if we consider only the first two, with these two boxes, if we consider, then we get x by d 1, this was 3. So here x is how much? L. So x by d will be L by 0.7. This is 1.43. And also y by 3 is L divided by 0.7 and u is also 1.43. So from here we get F13 is equal to F13 can be found out from here 1.43 and 1.43. So this is 1.43. Okay, my plot is wrong because I'm just doing it and just by manually. If you plot with scales and all, exactly if you want to find out, then you have to plot on the graph paper with scales. So this will come around 0.3. So this is 0.3. So from here we can calculate F12 is equal to 0.38 minus which it is 0.08. So like this we find out the view factor. So is it clear? Because it might be, maybe it might be taught in your college or it may not be. I don't know. But this is one of the methods by which we can estimate the view factor. Okay, the graph should be provided to you and you can easily find out. Just you have to know what you're exactly considering x and what you're considering this y and d. And according to that, you have to fit in the y by d ratio and x by d ratio here. And then whatever at which point they're joining the y by d and x by d, that from that point you have to draw perpendicular to the y-axis. And whatever you get there is the view factor of F12. And here also you have to see what you're which surface you're considering one, which surface you're considering this two. And then you can easily find out what is this, what is the view factor. So in the previous here we have considered two such configurations for x by d and y by d, so that you can understand because we have extended one part here and another part here. So some x by d and y by d ratios are changing here and here also. So according to whatever is required, we can manipulate the figure geometry according to our need. Okay, then we can find out the view factor. And another example is this: instead of simply a square shape, we can also find for such conical shape also. So here also we have standard these plots, and here again the same thing. We have to know what exactly we are considering. This R1 means surface 1 and surface 2, which we are considering, that we have to see. So first is a heater. So this is a heater as shown in the figure, radiates to the partially conical shield S that surrounds it. So the shield is given as this is the surrounding. Okay, it's a 3D structure. No? It's the shield. The curved surface part is the conical part. If the heater and shield are black, heater is the below one. H is given here. So both of them are black surface. Both the heater and the shield also. Calculate the net heat transfer from the heater to the shield. So how can we proceed here? Suppose that the shield was heating. Okay, this is the next part. So first we have to find out if the heater and shield are black, calculate the net heat transfer from the heater to the shield. It's Q H to S, heater to the shield. So for finding out QHS is equal to Since they're black surfaces, sigma A F H S T H to the power 4 minus T H to the power 4. So this is the heat radiated from heater to the shield. Okay. Now we know this is already a constant and area is the area of the heater. Okay, then the only thing we need to find out is the FHS. TH is already given 1200 degrees Celsius and TS is 100 degrees Celsius. So we need to find out what is FHS. So for finding out what is this FHS, we have, so the first surface one is the bottom and surface two is the upper part. So in our case also we can do like that. Only thing is that their surface one is bigger than surface two. Our surface two is smaller than their surface two. Anyways, that doesn't matter. The size doesn't matter. But so this is our just like I'm just imitating this, and this is our one. This diameter was given as 10 centimeter and 20 centimeter. So this R2 is R2 is 10 centimeter and R1 is 5 centimeter. So we need to find out what is this R2 by L and L by R1. L is given as 20 centimeter. So, so R2 by L is R2 is 10 and the L is 20. So we have it's 0.5 and L by R1, not R1 by L. L by R1 this is L is 20. R1 is 5. This is 4. Now from here, what do we get? R2 by L is 0.3, this R2 by L is 0.4, and this is 0.5. This is the graph which we need for R2 by L, and L by R1 is 4. That means this one here. So we just have to draw perpendicular to this and this point from here again perpendicular. So it will be around 0.2. This one. So this is F12. That means 1 to 2. Now if I consider in the figure in our question already this surface 1 is heater, that means it is H, and this curved surface part is shield S. But top surface they have not given anything. Suppose we are considering it as I, top surface is I. So this F12 is nothing but 1 is below 1, 2 is top 1. So F12 here is our FHI. Okay, so here what we get, this is 0.2. So we got this. Now we have F by summation rule, we have FHS So by summation rule, we have FHS plus FHI is equal to 1. So how much this H is radiating, it is received by the conical surface, that means this shield, and also by this top surface I. So FHS plus FHI is equal to 1. This is the complete radiation. So we have this FHI, we already calculated here 0.2. So FHS is 1 minus 0.2, 0.8. So we can now easily calculate what is QHS. This is sigma A. Sigma is 5.67 into 10 power minus 8. And A is the area of the heater. We have asked for heater, right? So area of the heater is pi d square. Since it is circle, so it is simply pi d square, pi into d is diameter of this is 10 centimeter, that is 0.1 pi d square by 4 into FHS, that is 0.8, and TH, my TH to the power 4 minus TS to the power 4. TH is 1200. This is in centimeter, sorry, Celsius. So we have to add. So you can calculate it, you will get around 1669.41 watt. Just calculate it while practicing. We also have the next question. Suppose that the shield was heating the region where the heater is presently located. That means the shield will be in the heating region. Shield was heating the region where, okay, now the shield is heating, not the heater. In the previous question, the heater was heating and that radiation is received by the top surface and also by the shield. Now the shield is radiating heat where the heater is presently located and it is received by the heater. So what will FSH be? We have to calculate this. So here, how do we proceed? We have, this is a summation rule. We also have the reciprocity rule. AS FSH is equal to AH HS. So we already know what is this FHS. We already found out. We know AH, that is pi d square by 4. Now, if we know what is AS, then we can easily find out this FSH. AS is nothing but this curved surface of this. So this is actually a frustum. And frustum area can be given as area of frustum can be given as frustum is the cut portion of maybe a cone, maybe pyramid. Okay, so this is a cut portion. If we draw a cone and if we cut here, then this is exactly what is called frustum. So this is So L is this. Sorry, this is L. And R2, R1, we know this is R2. This is R1. D1, D2 are the diameters. So like this, we get the area of frustum. So we can now calculate this F S H A H by AS into FHS. Now AH is ID square by 4. This was D1. So this is just solving it. So if you solve it, we know all the values. We know D1, we know D2, we know R1, R2, and L is also given. L is the height, that means 20 centimeter. This one 20 centimeter. If we substitute all this, we will get around 0.06. So FHS is 0.8 already found out here. We substitute all the values and we should get the value 0.06. You can just note it down and later you can calculate also. So here we have used the summation rule and also the reciprocity rule. So these are for view factors we use. We can frequently use this rule so that the question is simplified. So these are some standard graphs which are already available, and these are for not it's not present for all the any random shape, but then some shapes like this. One is the one one surface on top of the other, one rectangle on top of the other, and one here is one circle on top of the other. And if we get such combination of shapes in exam, we can use this graphs or plots. Then next we have another one. This is also the same like the previous one, the first question. Since these are two squares, it's not square but it's rectangle. So two parallel plates 0.5 by 1 meter are spaced 0.5 meter apart. One plate is maintained at 100,000 degrees Celsius and the other at 500. The emissivities of the plates are also given. The plates are located in a very large room, the walls of which are maintained at 27 degrees Celsius. The plates exchange heat with the, so this is placed in a large room. And the wall temperatures are maintained at 27 degrees Celsius. The plates exchange heat with each other and also with the room, but only the plate surfaces facing each other to be considered in the analysis. Find the net heat transfer rate to each plate and the room. Neglect other modes of heat transfer, for example, this conduction, convection. So this is one of the assumption that you can neglect conduction and convection. Now for such case, we will again follow the previous graph. Again, it's given here. So in this case, six, one, this is 0.5, and this is also 0.5. That means this is x, y, so x by t we have 1 divided by 0.5. This is equal to 2. In y by d we have 0.5 divided by 0.5. This is 1. So x by d 2 and this is 1. So 2 is already here. And this is the point where it meets with the y by t equal to 1. So if we draw perpendicular from here to the y-axis, we get around 0.285. So F1, if we consider this as surface 1, this as surface 2, F1 is 0.85. Okay, now from reciprocity rule we have, and also they are symmetric to each other. From there also we can write A1 and A2, they are of same area, so they get cancelled out, and F12 and F21, so they will remain same. You can also write this just by symmetry, directly by symmetry also you can write, since they have the same area and all. So whatever is F12 is equal to F21. Now we have this is a summation rule. Now 3, if we consider the bigger surface, the outer surface, that is 3, then we can write like this. They have told that the plates are located in a large room, so this room is considered to be the third surface. Okay, we can just assume it to be the third surface. Then we can write the total summation rule as this. Then from here, F11, it cannot see itself since it is a plane surface, so it is 0. Then F13 can be written as 1 minus F12, that equal to 1 minus 0.85. So this is equal to 0.715. Now what they have asked find the net heat transfer rate to each plate and the loop. So in such situation, we can draw resistance. Since there are more than two, we can draw the resistance diagram here. So this is surface 1, surface 2, and surface 3. That is the outer surface. That means the large one, which can be considered a black body also because it's the resistance is very less. So this can be considered a black body. And we have other resistances also. So these are known as the surface resistance. Surface resistance are because the surface is radiating, so they have some surface resistance, and there are also some space resistance which are due to the view factor. Okay, these resistances are due to view factor. How they are, one surface is emitting, another surface is receiving. How much fraction of that energy they're receiving? This is due to that view factor. Okay, so this resistance can be written as 1 minus epsilon 1 divided by A1 epsilon 1 This resistance can be written as 1 minus epsilon 2 A A2 epsilon 2. Suppose this is R1, this is R2. These three are suppose R12, R13, R14. So for the third point, third node also you can draw like this. But then here, since the room is very large, the resistance is very less. So this resistance is almost negligible. So we can directly write this EB3 as equal to J3. Okay. So now R12 is given as 1 by 2. This due to the Gibbs factors. All these resistance, these three resistances are due to Gibbs factors. Sorry, this is not R4. This is 3, this is 2. So it should be 2, 3. Now what are these? We found out, did we find out F12? Yeah, so we found out F12, we found out F13. And what is F23? 1 by A1 is, 1 is this. So this area is 1 into 0.5. That is 0.5 only. And F12 is 0.285. A1 is again 0.5. F13 is just 0.715. Now what is this F23? F23 is again by symmetry we can say, since this is the larger surface, this is 3. Now both of them are having the same area, 1 and 2. So F13 is also equal to F23. So by symmetry we can write F23. So we can write this as 1 divided by 0.5 into 0.715. Now next we have this more two resistances we have. This is 1 minus epsilon. Epsilon is given here. So remember that 1 is, we consider the below surface here, but it's given 2. But anyways, you can ignore this and you can make your own notations also. Since we have been considering the below one as 1, so the below one is having 0.5 emissivity and the upper one is 0.2. This is 1 minus 0.2. So at this node, first we have to calculate all this. Then at this node, first at node J1, we have, so this is just like electricity, that electric circuit, I mean, the circuit resistance diagram. Suppose we have this energy coming here from here, it is getting distributed to this and this. So we can write as EB1 minus J1 divided by the resistance, that is R1, is equal to J1 minus J2 or J2 minus J1, anything. J2 minus J1 divided by R12 plus J3 minus J1 divided by R13. So this is one equation. Another equation we have here, J2 at node J2. We can write same thing, EB2 minus J2 divided by R2 is equal to J1 minus J2 divided by R12 plus J3 minus J2 divided by R3. Now if we solve this equation, we can get the values of J1 and J2. In this equation, we are already calculating this R1. R1 we know, R12 we know, R13. So all these equations, if you solve, you'll get the values of R1, R2, R12, R13, and R23. Okay. Then we also know what else we know. We know EB1 and EB2. These are black bodies. So this is 1000. This is 500. We can calculate EB1 and EB2. Into 1000 is you have to get you have to convert into Kelvin. There you get some values. EB is sigma T equal to 4. So the below one was 500, right? This should be EB2. Because we have considered one as the below surface and two as the upper surface. So here again you get some values. And then we have another, we also know what is J3, okay? J3 is EB3. J3 is EB3 is equal to sigma T3 to the power 4. T3 is also given here. The room temperature, that is 27 degrees Celsius. So 27 plus 273, you get 300. 300 to the power 4. So again, you'll get some values. Now, if you solve all this, we have two variables, J1 and J2. And we have two equations. From two equations, you can get J1 and J2. So J1, you get around 33.469. And J2, you get around, this is kilowatt per meter square. Now, so total loss by plate 1. So what they have asked, net heat transfer rate to each plate and the room. So we have to find out Q1, Q2, and Q3.
And can I say something? Am I audible? Yes. Can I say something?
Q2 is equal to Q3 is Q3 is already J1. J1 minus J3 divided by R1, or you can write J2 minus J3 divided by R23, any one equal. So these are the heat transfer. These are the net heat transfer rate to each room, each plate and the room. So this is from this is between one and room, plate one and room, this plate two and room, and these are among the plates, in between the plates themselves. So like this we can get the heat transfer. So we have to take the help of this view factor, because this is also one of the resistance faced by the this radiation on the plate surface. So the next question is about, okay, this is something it may or may not be taught. I don't know. This using the epsilon NTU method, and this is for more than one number of shell pass. This is for two shells. So for a just for quick, uh, briefly, I'll tell you what is this. A shell and tube exchanger, two shells and four tube passes, is used to heat 10,000 kg per hour of pressurized water from 35 to 120 degrees Celsius with 5,000 kg per hour pressurized water entering the exchanger at 300 degrees Celsius. So since it is used to heat this, so this is the cold fluid. Cold fluid is 10,000 kg per hour. So you have to take a very careful note of this unit also. You have to convert this into SI unit. So SI unit will be kg per second. So 10,000 divided by 300, 3,600. Okay, then we have the MH mass flow rate of this hot water is this 5,000 by 3600 kg per second. Entering the heat exchanger at 300. So THI is 300 degrees Celsius. Then TCI is 35 degrees Celsius. Then TC naught is 120 degrees Celsius. And if the overall TH naught is not given here, so how to find TH naught? Just do MCP del T from both sides of both fluids. MCP C delta TC is equal to MCP of hot fluid delta T hot. So from here you get TH naught, and overall heat transfer coefficient U is given here. U is 1500 watt per meter square Kelvin. Now determine the required heat exchanger area. So finding out the heat exchanger area, we have to, with NTU method, how do you get? So NTU is given by AU divided by C mean. C mean means MCP mean. So whichever fluid is having the minimum MCP, you will consider that. So for you first calculate for MCP cold, for cold fluid you will get some value, and for hot fluid you will get another value. Okay, you compare this two and you see whichever is the minimum that you have to insert here. Then you know you have to find out A. A is what they have asked to find out, and determine the exchanger area. So A you have to find out, and before that you need to find out this NTU. NTU is how much? So for finding out NTU, you have to, there are series of formula related with that. First you have to find out the capacity ratio, that is C mean divided by C max. So whichever is the mean, that will be on top, and whichever is the maximum will be at the bottom. So you'll get a value of CR. Now that CR you will use for,
Excuse me, ma'am. Ma'am, can I say something?
okay, but before using that, there is effectiveness also, which is given by Q divided by Q max. So Q, you can find out Q by any of this, either this MCP delta T for cold or MCP delta T for hot fluid. So any one of them you can use for finding out the Q. Then Q max is given by C mean into delta T max. Now C mean is already from here, whichever is the mean that will come here, and delta T max is given by uh, THI minus TCI. So this is fixed. This delta T max is fixed. So you'll get some value of epsilon. Now you'll put that this value in this equation. So since this is two shell passes, so first you have to find out for one shell pass, and this is given by 1 plus CR square e power minus half into ln e minus 1 divided by e plus 1. So this e value is already given here. This is 3.29. So if we put the values, this e value is 3.29. If we substitute all the values, we already know what is CR also. This is the CR. If we put all the values, we will get another value. Then the final NTU will be N, and this N is 2 because there are two shell passes. This N is equal to 2. 2 into how much we get for this NTU for first shell pass. Okay. Then we get some value like 1.10 around. Then this NTU value you substitute here. Okay, so we can find out A, which is given by NTU. Saying something? Hello? You're saying something? Yes. April. Okay, you didn't watch any of the lectures. I mean, main uh, for heat transfer, you're asking? No. Main topics. The first is heat transfer. If I divide, then it is divided into three modes of heat transfer that you know, con conduction, convection, and radiation. And in conduction, there will be uh, not conduction problems are mostly easy only. I mean, I also forgot what numericals I have done. It's been almost 3-4 months in this. We have been doing this. So there will be some in conduction. There will be some resistances problem. Okay, you will get 1 minute. So you'll get some problems like this, some like this, and some maybe like this, like this. So these are resistances problems. These are in, just like we have done just now, we have done for radiation also, that resistances problem. So this will be in series, this two and this two will be in parallel. So we have to draw parallel like this, and then again this will be in series. So mostly in such compact, what is this design called? I forgot what is it called. But then in such cases, if there are more than one uh, type of material, then you can use this resistance formulation. Then you can easily find out what is the heat transfer rate, or whatever they are asking to find out. You know how to find out for plain valve, for cylinder, for spherical, what is the resistance. You'll get in the books and all, or in the lectures also, for what is the resistance for each of them. So Q is given by the driving force. Driving force is the temperature difference. Okay, so between this and so this divided by resistance. So this is the formula for resistances. And in some cases it will be series, some it will be parallel. So you can get that how to do that. Then we have this critical radius problem also. I was just going to do, but uh, okay. So it must be done in a college also maybe. So this critical radius, you know now what is this? So it is just the outer, how much insulation it is you are required to give to a certain material. Okay, so that there is minimum loss. And so sometimes we have to give, I mean, the cost consideration. In some uh, material, in some applications you will require more insulation, in some applications you will require lesser insulation, and everything, all other engineering aspects also you have to see. Then that's why we require this critical radius uh, calculation. And then we have in radiation, what else we have? Sorry, in conduction. No, I think this is pretty much in conduction. Then for convection, we have this free convection and forced convection. Okay. Then in forced convection, there are, this convection is totally related. I mean, these you can mostly you are required to find out what is the heat transfer coefficient for convection related problems. And this H is usually have to find from correlations. These are mostly based on correlation, because it is very difficult to find some formulate a particular formula for this convection part. So I mean, different researchers have given different correlations based on different conditions. So you should know which correlation to use in which condition. For force it is something, for free it is something, and for laminar region it is something, for turbulent region it is something, and it is a mixture of all. So you have to mainly know what are the conditions. These very important conditions at which you will use these relations. Which week I have done this? Okay, there are different geometry also for this convection. It may be flow past a flat plate, it may be flow past a cylinder. So those are also important conditions, which at which condition you'll use which. Then you have to go through these numbers, this Prandtl number, Nusselt number. You have to know all this. Have you come across these terms? Reynolds number, Prandtl number, Nusselt number. Reynolds is pretty much, this is the most basic uh, dimensionless number in fluid mechanics or in heat transfer, Reynolds number. After Reynolds number comes the Prandtl number and Nusselt number. Then we have, just go through these numbers. Okay, these are, you have to know the significance also for these numbers. Then flow through pipe. So after this flat plate is the next one is the pipe. For pipe, we have this Cedar-Tate equation. Then we also have, if it is turbulent, if it is laminar, what it should be. We can use, for turbulent, we can use the Ditus-Boelter equation. This is very much used, this Ditus-Boelter equations and all. So please go through this. It's very common equation. Once you calculate the Nusselt number, various correlations are given for Nusselt number. Once you get that, you can calculate the the heat transfer coefficient from that. Then, then we have the convection and boiling also. For boiling, there is a boiling curve which you should go through. That is also very important. There is a boiling curve. There is some region of nucleate boiling, pool boiling. Okay, so you have to know every region. And then this is, if your exam is on 18th, then you have only 4 days. 4 days, how will you Yeah, available on the screen means on your, yeah, if you are, I mean, maybe some colleges do not teach this part, may some colleges teach this part. So I'm not sure if your college has taught this. I mean, view factor you can measure anyhow with, okay, okay. NPTEL, but okay, you're talking about but NPTEL, I think this was not taught. I'm teaching it from myself only. I mean, in from one of the books. So this is this. How to summarize all everything in. If you have told before, then little bit I could prepare. But now suddenly, uh, no. This is only the last. This is, yeah. So actually, last class was on last Saturday. Okay, then they have asked for one more this extra class. So today is the extra class which I took, and 14 is the last day for this. Huh. So radiation, huh, Yeah. These are same. I have my, yeah, you can score. Anyway, this my lectures. I mean, my lectures are available on YouTube, I think. So you can go through that. I mean, sir's lecture will be around 60 hours, no? Mine will be around 12 lectures I took. So only problem solving sessions we have done as TA. So there were 12 classes into two, around 24 lectures. Sorry, 24 hours. If you see even those also, I think it will be fine. If you can't see 60 lectures, then you can see the problem solving ones. But once in a while, you should go through those lectures also. Okay, but just for problem solving, you can see in my, I mean, that YouTube videos. Those are only for 24 hours because 12 lectures we do each for 2 hours. So those are solely based on NPTEL only. Only 2 days extra class I took little bit something from books part. Uh, yeah. What else? Yeah. Sorry, I couldn't help you. I mean, this is how much I could tell. Huh. Resistance is just, I mean, for every heat transfer, there is some resistance for both, for all three, for conduction also, convection also, radiation also. It is just a easy method to find out the heat transfer rate. It's not easy method, it is only the method because all the heat transfer, they face resistance. Yeah, for convection, you need to be little bit, I mean, a little bit more, this is, concept is required for convection part. And resistance sorry, radiation, there are uh, two methods. I mean, last class I have done this shell and tube heat exchangers and all. So for that you have to go through that LMTD, delta T, LMTD, log mean temperature difference. And another method is the these are just to find out the temperature, okay? Because this shell and tube, this not only shell and tube, whatever heat exchangers are there, there are inlet and outlet temperature of hot fluid and inlet outlet temperature of cold fluid also. This LMTD is used to find out one of, I mean, those temperatures. And also this, you can use this NTU method also. This is also one of the method to find out the temperatures. And the radiation also, it has these view factors which I have done. It has radiation shield and it has different laws actually. Stephen Boltzmann's law and Wien's displacement law, Planck's law. These are some small topics in radiation which I would say. Yeah, so this is pretty much it. You have any more questions? Okay, try to solve those questions, and you can also see the lectures. Okay, in YouTube, my lectures are available. I mean the these problem solving lectures. Okay, okay. Should we end? I mean, this was only for one. This was you are what you said. I didn't get. Ha, actually, this was for 1 hour only. Yeah. No, no problem. If you want, I can complete this also. This is another question which I had. This for critical radius. Critical radius is saying it is very. Now it's visible. So critical radius is simple only. It is just you have to use this formula K by H. K is the conductivity and H is the heat transfer coefficient. And you can directly find out the RC. And RC is the radius, okay? Radius of uh, critical radius of insulation. For finding out the thickness, you have to find out RC minus whatever is the radius. If this is the radius of the pipe and this is the radius of the insulation. So this is the radius of this is RC and this is R. So the thickness will be RC minus R. Only this is the thickness, right? So this only. And in engineering problems, you need to I mean, some silly problems, silly mistakes are mainly done in the units. You have to check the units very carefully, okay? If you're solving in SI unit, then all the units should be in SI. So this is one issue. Okay, should I solve this problem? Okay. This is a silicone coating. This insulation is used with an 8 millimeter diameter copper wire whose surface is maintained at 210 degrees Celsius by the passage of an electric current. So this is the copper wire. This inner one is the copper wire and it has a diameter of 8 millimeter and it should be maintained at 210 degrees Celsius. So why this insulation is used, these coatings and all are used so that it is maintained because with the surroundings it will interact and there will be some heat exchange. So this temperature will not be maintained if there is no insulation. So to maintain such temperature, they need to coat it. The wire is placed in an ambient air of 30 degrees Celsius and the convection coefficient is 120 watt per meter square Kelvin. So this is what is H. This is H of coefficient of the air, the surrounding air, ambient air. What is the critical radius associated with the coating? And what is the heat transfer rate per unit length for the bare wire and for the wire with the silicone coating? So first is critical radius. This is how we find out RC. RC is equal to K by H. K is given as 0.6 and H is given as 120. So if you calculate this, you will get around 0.005 meter. So this is RC. This is the answer for the first question. What is the critical radius associated with the coating? So you have to be very careful whether they're asking radius or thickness. So radius and thickness both are not same. Radius is this and thickness is calculated by this RC minus R. Then the next question is what is the heat transfer rate per unit length for the bare wire? That means without the coating and the wire with silicone coating. So you have to compare both the heat transfer rate for both bare and with coating corresponding to the critical radius. Okay, so first we calculate this by Q bare is given by delta T. Since there are Q bare means there is only electric wire. There is no insulation on top of this. So here the driving force is delta T and what is the resistance here? The resistance is only this convection part. So it is 1 by HA. So area is the curved surface area of this, not the um, not the upper portion, upper circle. Why it is a curved surface area? Because heat is getting transferred from this curved portion only. So it will be A will be of for cylinder. A is how much curved surface area is pi RL, 2 pi RL, right? This is the surface area. So how much we get this? So this will go on top H 2 pi RL into delta T. Delta T is surrounding this inside temperature minus the surrounding temperature. So we have all this. We know what is H. H is also given here. H is 120 watt per meter square Kelvin. Then pi is constant. R is diameter is 8 meters, so R is 4 millimeter. So you have to take note of this unit also. It should be 0.004 meter because it is 4 millimeter. Then L is not given here. The length is not given, but we can consider it as unit length. So in the question also they have given what is the heat transfer rate per unit length. So you can consider it as one only. And delta T is 210 minus 30. So 180 degrees Celsius. So you have all the values, you can calculate Q there. So this will come out to be around 542.6 watt per meter. And then we have and then we have without insulation we have calculate, and now we will calculate with insulation. So here this is the wire. Now we are putting an insulation here. So some resistance will come because of this coating also. So there are two resistances now. So this coating, since it is, I mean, this is a solid part, so it will be conduction. The resistance will be due to conduction. So delta T is here, and there are two resistances. One is conduction and one is convection here. So for conduction, for cylindrical, it is ln RC by RI. RC why I took because this is the critical radius divided by 2 pi KL plus 1 by H. Now this A will be, in the previous case, this A was only 2 pi RL. But here now the outer radius is RC. So it should be 2 pi RC into L. The radius is changed now. The outer radius is now RC. Now again you have to calculate. This is 120 minus 30 ln RC we have calculated already. 0.005 divided by RI is 0.004 divided by 2 pi. A is 0.6 and L is 1 plus 1 divided by H. H is 120 into pi. RC is 0.005 into 1. So if you calculate all this, you get Q insulation as 555.55 watt per meter. So we get this Q insulation. With insulation, we have 555.55. But without insulation, we have 542.6. That means with insulation, With insulation, the heat transfer is increasing. So what does it mean? This is Q, this is radius. So the graph for critical radius is somewhat like this. At this point, the Q is max. The heat transfer is maximum at this point. So this is which point this R equal to RC. So at critical radius it has this definition that the heat transfer is maximum. So you should avoid that region so that you can design your equipment in such a way that it is either here or here, so that there is minimum loss of heat, either this side, this part or this part. So if you take cost consideration, you have to consider this part because you need lesser material for insulation. Okay, now this is what they have asked. We have found out already what is the heat transfer rate for bare wire and for coated wire. Another question is what is the thickness of silicone should be added to reduce the heat transfer associated with the bare rod by 10%. So for bare rod, the Q was this much. 10% loss means 10% less means 10% of Q bare is equal to, so this will be 54.26. And how much is this? 5.6 minus 24.26. So this is equal to 488.34 watt per meter. Now to find out, so that the heat transfer rate is this much, R should be how much? This is what they have asked. So again, you have to make such. So we have Q is equal to delta T divided by. So here everything you know except this RC. RC is gonna, it will be changed here because we need to find the new RC here. So for finding out RC, again is the same thing, only ln, instead of RC you can write R, and you can write this is the Ri is fixed only 0.004, then 2 pi KL plus 1 by H. A is 2 pi R into L. Now from this you know everything. Delta T is this only 210 minus 30. Then Ri is 0.004. K you know, L also, L is 1. Then H also we know, 2 pi. L again we know. So here also there is R, here also there is R. So this is not that easy to find out because it is inside log scale, ln is there. So we have to find it out by trial and error method. For after finding out by trial and error method, this R comes out to be around 0.055 meter. Sorry, 0.0095 meter you get. And the critical thickness, this is the R which is found out, and the thickness is RC minus R. So they have asked to find out what is the thickness. Thickness should be RC minus R. RC is 0.0095 minus 0.004. So it is 0.0055. So I have done it little bit messy. To summarize, I'm telling you once again. So first is you have to find out the critical radius, which is very easy. Just K divided by H you have to do. The next is to find out the heat transfer for bare, means without insulation. Without insulation, you have to consider only the uh, convection convective resistance. Okay, but with insulation there is some material also coming into the picture, so it will be conductive resistance, so you have to add the conductive resistance also. For cylinder it is like this. You have to see for sphere it is something else. For plain wall surface the formula is something else, but this is for cylinder because we are dealing with cylinder now. And for convection resistance this already this. Then you can find out the Q insulation. And the last question is, what thickness of silicone should be added to reduce the heat transfer associated with bare rod by 10%? So bare rod was this much. If you reduce this by 10%, you just subtract the 10% of this, so you get around 488. So to get that Q, get that heat transfer rate, how much thickness you should add? So again, by this formula, by this same formula, only you will have to find out what is the RC. Then once you find out the RC, you just subtract the R, the inner radius from that, then you get the thickness. So you got it, right? I'm going too fast. You got this? Hello. Okay. Do you have any more doubts? Then if you don't have, then we can end. Okay. So your exam on 18th is for NPTEL or your college exam it is? Oh, okay, okay. Which college you are in? Okay, okay. It is in Jharkhand, but Bihar. Okay, 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 okay. Fine. You can just search in YouTube this problem solving lectures. Then you can go through this. Okay, all the best then. Okay, I'll end for today. Okay, thank you.